yes ใช่ yes and yes check the sound test 1 2 3 test 1 okay yes you have to throw away the file to no this one to the iPad the new version to add this oh we have to save the yeah it has been already saved yes already saved yes okay to iPad to data of my iPad this one I think okay oh no this 7 assets in application of iPad then one step this one we have to delete change the name right without to okay yes and here we open new okay new oh no new no import here from my iPad Suankularb 7 which one is the newest อ้าวไปไหนแล้วส่งมาให้ตะกี้นะครับ where is that my one here iPad that I my iPad and this one 7 okay great now we're gonna open right what's that right here okay this is for M604 นะครับผมไฟล์อัปเดตขึ้นมาเรื่อยๆนะครับก็เลยต้องเอาเวอร์ชันใหม่ที่สุดนะครับเนื้อหายังไม่สิ้นสุดนะครับเตรียมได้เท่าที่เวลามีนะ M604 and today is 26.01.2022 okay yes good afternoon everybody we are late for 6 minutes we're gonna have the compensating time for also for 6 minutes because M604 is quite behind M605 1 or 2 periods of our lecture so let's talk about our story. Yes, you have written your name in the office. I don't understand why ว่าเกิดอะไรขึ้นWhat's the reason? Okay. ไม่รู้ว่าหายแล้วหรือยังครับ Okay. In for M604 we alive somehow ถึงตอนไหนครับมีคนไหนจำได้ไหมเอ่ย I think you are quite lag behind the I hope it's somehow it's like M604 right มีคนไหนจำได้ไหมครับเราถึงตรงไหนกันเลยotherwise I'm gonna open the file in Google Classroom in Google Classroom in this is good and we open this one, Google Classroom Google Classroom M604 right yeah for the SK right อันนั้นมันกระพริบยังไงไม่ทราบครับnot sure this is well blocking M604 right classwork for us in the last last time I don't know we realized it somehow okay we live at the gamma decay right and we're gonna start our lecture on carbon dating right carbon dating that's the result from 20 January right so good afternoon officially we now will start our lecture on this อันนี้มันกระพริบนะครับผมไม่ค่อยชอบ all right even we don't have the I hope it's better right it's gonna be better นะครับน่าจะดีกว่าอันนี้ดีกว่าโอเค I'm gonna use this instead okay yes the carbon dating right it's the story about to determine the age of something in the past these objects should be the organism object okay it's not any object you should the object should be something from organism whether it's plant or animal or human being like us okay yeah carbon dating is one of the major topic in nuclear physics because this is the straight application of what we have seen in the story of half-life okay you have ever determined half-life right the amount of time that something disappear by half all right let's start with this topic carbon dating in the main object that we will use is the same thing the main object we're going to use is the carbon 14 okay carbon 14 is the major component to us in this story you know that carbon has three major isotopes right carbon 12 carbon 13 and carbon 14 right yeah carbon 14 is the object that we pay attention to determine how long or what is the age of that ancient object which is a part of organism okay carbon 14 is unstable as you know when the nucleus is too big too great okay it might not be stable and that also holds for carbon element okay carbon 12 is the most stable one, but carbon 14, which has 2 more neutrons, is not good at all. All right, we're gonna see how we would have to thank to the scientists because they are quite clever to observe this stuff. Okay, yes, carbon 14 has the half-life of 5,730 years and plus and minus 40. In some sources, they might say it's exactly 5,730 years, but I found that there is some errors because according to the recent information, human has done something like has made the experiment of nuclear bomb and so on. So the amount of carbon in nature has changed a little bit. So there might be some error, which is 5,730. Okay, and let's talk about more detail. In our world, the carbon 14 is created by cosmic rays. So it's the result in the atmosphere. Okay, and in that layer, in the layer of a troposphere and stratosphere. Okay, this one. Okay, according to this figure, yes, the half-life is around 5,000, right? And the cosmic rays are the high energy ray that contains some particles too. That is emitted from somewhere else out of the world, and it's from deep space, okay, from other stars, from stellar, from other planets, and this is the high energy ray. So what we could do is that we could not do anything, right? It just take place in nature, but the scientists or the physicists have found it. Okay, it's the high energy particles from outer space, from deep space, okay, in from the nitrogen 14, okay, it's the same number of nucleons, the atomic mass, yes, the mass number as same as carbon 14. The nitrogen 14 that happens in the atmosphere, that exists in the atmosphere, okay, got the neutron from the cosmic ray. Cosmic ray hit something in our atmosphere, and after that the neutron is created. Several neutrons are created actually. So the neutron would have kinetic energy, right? The main story in physics. With the kinetic energy, neutron will hit nitrogen 14, and from what we have seen here, the nitrogen it will be transformed to something else, and on the right hand side, this is the result, okay, from this process. It is a kind of beta decay. Okay, nitrogen has been created according to this process. In more detail, nitrogen is converted to carbon 14 with one additional proton. Okay, neutron has been converted to be right. It's to be proton, right? Neutron. No. It's 14, and the number of protons here is 7. The number of protons here is 6, and one proton has been kicked out from the nucleus, and the number of nucleons is the same, 15 above and 7 here. Okay, proton has been kicked out, neutron has been converted to proton, and in the upper atmosphere, which is around 9 to 5 kilometer above the ground. Okay, we measured from the ground like 9 to 15 kilometers, and yeah, this process just take place, and yeah, we're gonna see what happens later. Yeah, carbon-14 has been created from the atmosphere in our world on Earth, and is sometimes fall down to the ground, and yeah, it can be combined in chemical process to oxygen, right? And we would have yeah, the well-known gas, which is carbon dioxide, 2 atoms from oxygen and 1 atom from carbon. We got CO2 like this, right? And CO2 is the gas that could exist in many applications, right? In many metabolism or consumption for whether plant or animal or human being. And one of the things is that when the plants absorb the carbon dioxide for their chlorophyll process, and yeah, this is the photosynthetic process. Yes, yes, the human or the animal. Okay, let's say we have a cow, and the cow is going to eat grass on the ground, right? And yeah, we have again the beef, which is the meat of the cow, and yeah, carbon-14, which will be absorbed to plus in our body, and that's the story that take place. Okay, because carbon-14 is not stable as it is mentioned here. It's not stable. It's a radioactive element. Okay, and with the half-life somehow for some time it's going to transform to nitrogen, and the process is what you may have seen previously, and yeah, the carbon-14 is going to be transformed to nitrogen again. It's beta decay here. Okay, we're gonna get the electron, right? It's beta minus process. Yeah, that's the beta minus process that you have seen. Okay, this is one of the process that could take place. Okay, yes, this is the creation of carbon-14 in the atmosphere of our world. Neutron from the cosmic radiation hit the nucleus of nitrogen-14. You know that in the air there are somehow like 80% of nitrogen, right, on Earth, and yeah, nitrogen is a big part of our air, right? We should keep in mind that story. What happened? Okay, yeah, the nitrogen will be combined to with nitrogen to become carbon-14, and we get proton. Okay, and once the animal or the plants absorb the carbon-14, we're gonna have the carbon-14, carbon dioxide 14 into the plant, and the animal or the human being eat the plants or the meat from the cow. So carbon-14 is transferred to our body, not only to human being body, but also animal body and any other wood or tree and so on, right? Yeah, that's the thing happen in nature. So we could not avoid this because it's take place, and once we are alive, we breathe, right? We take the air into our body, and we have the food every day, and the food contain carbon-14. So once you are still alive, your body still get absorbed to carbon 14. Okay, your body is still consuming or taking the carbon 14 into your body. So the rates of carbon 14 flowing into your body and the rates of carbon 14 that diffuse to nitrogen 14 according to this process. This is the carbon 14 decay process. Will remain constant. Okay, once you are still alive, but once you have passed away, once your body is dead, is died. So there is no amount of carbon taken into your body anymore because you don't breathe anymore. You don't take the food inside your body anymore. And that's the thing. The amount of carbon 14 is gonna disappear more and more inside your body once you have passed away already. Right? Not only our body, but also animal body or even the tree. Okay, and the scientist is clever. They use this amount to observe whether that object lasts quite long already or it's just a new thing. So we have to thank to the clever people who use this ratio. Okay, this is the generation process. This is the decay process of the carbon 14 in this is in the stratosphere, troposphere. This is on Earth, in our body, in here, animal body, inside the trees, and so on. Okay, this is what you have already seen. This is the beta minus decay because we got the outcome. We get the outcome as electron, which is beta minus, and we got also the electron antineutrino nu bar, right? Okay. Yeah, the theory you have seen take place really in nature. Okay, now is the time to see the nitrogen 14 that exists everywhere, right? On Earth, in the stratosphere, or in the troposphere. Yes, they combine to they combine together with the neutron, high energy neutron in the troposphere and stratosphere, and the result turns to be carbon 14 plus proton, and this carbon 14 is absorbed in terms of carbon dioxide to our plant, to our animal, and also to human body, right? Yes, we cannot avoid this in and that's the thing. Once you observe this, there will be cycle like this. Okay, the carbon 14 is absorbed into your body, and our body, the carbon 14 inside our body will take the decay process, right? Because it has half-life and it turns to be nitrogen 14. Okay, this cycle will take place all the time. Once we are still living, okay, we are still breathing, we are still having some food, or not only for human, animal too, or even the plants. Okay, any organism, right, will have this process. Okay, yes. The thing that happens like that, and we could not avoid. Once, let's get to the number 3 here, and the usually in nature the number of the amount of it's more, right? More of carbon 12 and more of carbon 14. Okay, the amount in chemistry of any substance. The amount of carbon 12 is, I don't know, million is 10 to 12. I don't know how to say in English. Is million of million, okay, million more of carbon-14. So in 1 million molecule of carbon on Earth, you may find only 1 molecule of carbon-14, which is very extremely rare, okay, but at least it exists in nature. This will hold in nature, and once your body, my body too, or even animal body or the plant, okay, has passed away, has died, so the amount of carbon-14 is going to be reduced. So this one will disappear more and more, right? They use this arrow. It means that this one is gonna disappear according to this process, okay? Because the second process means the carbon-14 turns to be nitrogen-14, okay? That's the nature of carbon-14. Okay, this human absorb carbon-14 and they have the same ratio between carbon-14 and carbon-12, 1 by 1 million, okay, all the time. Because they continuously exchange carbon dioxide with their surroundings, so we breathe, right? And when an organism dies or passes away, that body, the plant, the animal or human body could not absorb the carbon-14 from the atmosphere anymore. So what happens? Carbon-14 will gradually decays. So with a half-life of 5,030 years. So if your body has passed away 5,730 years, okay, the amount of carbon-14 in your body will disappear by half, okay? It remains only half of the beginning. Okay, so the ratio of carbon-14 to carbon-12 will decrease, okay, will reduce all the time. According to the beta decay process of carbon-14, this process, the second process to become beta minus, lay and electron neutrino. Okay, by measuring the proportion of carbon-14 that remains, we can determine how long the organism has passed away. Okay, it is possible to determine the age of a material. Material now can be used, right? Because once we have passed away, once we have died, so it's no longer a human body, right? We can say it's a material. Yeah, the age of the material can be calculated by the activity. The decay rate, right? Activity is the absolute value of the decay rate per unit mass, and that's the result from the decay of carbon-14. Okay, let's consider the first example. The activity of the atmospheric carbon due to the presence of carbon-14 is around 0.255 becquerel, right? Becquerel is the basic unit in decay process, right? In radio decay, in nuclear decay. Okay, Curie is the scaled version, right? Becquerel is the first person who observed the nucleus that disappear, right? So Becquerel is this nuclear per second, right? So it's the rate of change of the disappearing nucleus of any atom. So 0.255, that's the rate of the carbon-14 per gram of carbon. Okay, this is for carbon. And what fraction of carbon atoms are the carbon-14? That's the first question. And the second question is, if the activity of an archaeological specimen is 0.0637 becquerel per gram, what is its approximate age, the approximate age of the archaeological specimen? Okay, they have found an ancient object, and the scientist has found also the decay, the activity, which is the absolute value of the decay rate as 0.0637. Actually, it's negative value, right? But actually, it's only the absolute value, so we take only the positive number here. We need to determine the age of this ancient object. Okay, so that's the second question. Okay, we have to borrow the idea from chemistry, right? The mass of the Avogadro's number of the carbon-12 isotope could be found by this relation, right? Na is the Avogadro number, right? It's 6.022 10 to 23 atoms per mole. Okay, we have to go to mole unit. And for carbon-12, it is the basic thing, right? Basic thing to chemistry measurement of any atom, right? Because one atomic mass unit is equal to 1/12 of the carbon-12 atom, right? So for carbon-12, the mass in atomic mass unit of the carbon-12 per atom will be simply 12. Okay, exactly, because that's the reference element to this one, right? So yes. The next one is the amounts of mass per atomic mass units, which is 1.660538 10 to negative 24. Okay, 10 to negative 24 gram per unit. Okay, that's the conversion from atomic mass unit to the typical unit of the mass. But in chemistry, okay, it's in gram, it's not in physics. Physics will say something about kilogram. Okay, this is the basic value. You just browse or take it from the beginning of this chapter. This is the mass of the carbon-12, right? It's used as a reference. We could not have any other value than that, because carbon-12 is the reference element. So once you put these three things, okay, Na is Avogadro number, right? You put these three things into the calculator, you're gonna get the results. Okay, you're gonna get the results, and yes, it will be 11.99712, but actually it's approximately 12. Okay, 12 gram per mole. Okay, 12 gram per mole in chemistry, right? Okay. What else? The next one is that in the standard, carbon-12 is approximately 12 gram per mole. Okay, from these results in the mass of carbon-12 of 1 gram is equal to 1/12 mole, and in 1 gram we're gonna have 1/12 mole. So 1/12 times the number, the Avogadro number, right? It's 6.02 10 to 23. I don't know, million 4 times, almost 4 times. And we will get 5.01833 10 to 12 atoms, okay? From only 1 gram of the carbon-12, we have number of atoms like this, okay? Very large amount. Okay, the number of, let's go to carbon-14, okay? The isotope, the major isotope for us in this one, okay? Yes, the carbon-14 could be found from the rate, right? The number of carbon-14 will be the number of atoms of carbon-14 will be the rate of change of the decay of the nucleus, right? And it's multiplied by the decay rate lambda, right? Decay constant. So we can convert decay constant into the half-life term like this, okay, ln 2 by t1 by 2, t period, right, which is the value of half-life. Okay, ln 2 is 0.693 approximately. And this is the rate of change they have provided here, 0.255 nuclei per time. Okay, yes, the next one is we have to substitute, right? We have to transform the half-life in years. I don't know. We have to finish this section at 14, right? 14. Okay. The half-life from years, 5,730 years to become second, right? You have to multiply it. Okay, t by period, t and the half-life at the denominator becomes the numerator, right? It just appear here. Okay, we have to convert the half-life of the carbon-14. We don't use plus and minus 40 years, okay? We simply use the 5,730. That's the standard value to everywhere. So we have to use this one, 5,730, convert it to seconds. How could we do that? If we use approximately every year, there are 365 days, and every day there are 24 hours, and in 1 hour there are 60 minutes, right? And in 1 minute there are 60 seconds, right? Yeah, we use this way to convert the half-life of the carbon-14 to become second. And yeah, ln 2 will remain the same, and the rate of change of the nucleus will be a negative value, which this is the information the problem has provided, 0.255. All right, becquerel means nuclei per second, right? Or decay per second. We have to use the negative value because it disappears. Okay, the amount of something disappear, we're gonna use the negative value. Okay, we cannot avoid that. Okay, yeah. The next thing,ผมขออนุญาตสังเกตคุณในไลน์ก่อนนะว่ามีใครเป็นอะไรหรือเปล่าครับคุณพิมพ์มาว่าเข้าซูมเข้าอะไรนะครับ Okay, negative value and negative value will turn to be positive value. So we have the number of carbon-14 like this. It's 6.6. 6.6. It's a large amount, right? It's I don't know. It's 10 to 10, okay, which is very, very, very large. But as I told you, the number of carbon-12 is million times higher than the number of carbon-14. You can see here, if you divide these two numbers, 10 to 22 divided by 10 to 10, it's going to remain 10 to 12. Right? As I told you, it's 1 million times higher for carbon-12. That's the typical isotope of carbon. But this one is the radioactive version of the carbon. It's radioactive isotope of the carbon-12. So it's rare. It's difficult to find because it's already disappear. Okay, turns to be nitrogen-14. Blah blah blah. Yeah, it's in the correct scale, right? 10 to 10 atoms, and we are gonna have the ratio because they want to find the fraction, right? The ratio of carbon atom of carbon-14. So carbon-14 divided by the amount of carbon-14, the number of atoms, exactly, actually. The number of atoms of carbon-14, which is this number, we found from the rate of change, and the number of carbon we found from the Avogadro number, right? And yeah, we make the division, and we got the ratio, which is very rare, right? In almost 1 million pieces of carbon, we're gonna find only one single carbon atom of 14. carbon 14 atom. Okay, that's the ratio and that's we could deliver. And note that our specimen divided by the rate of change of specimen is 0.0637, right? This is the amount of rate of change in from the problem, and rate of change of carbon 14 is 0.255, which is this value, right? So we got the ratio R specimen by 0.25 actually. So in order to find the age of that archaeological object, we transform the decay constant times the number of the nuclei into this one. Okay, N0 is the initial amount of nuclei. Okay, yes, the next one is that our specimen will be the decay rate of carbon 14 to the half-life, right? 1/2 T by half-life, and we convert number 2 to the numerator, which power is negative power, right? So negative will appear here, and after that we got this ratio from equation 76, and we leave the number here, the ratio, and we take the natural logarithm to both sides. Okay, we get the natural logarithm, and according to logarithm function, this one will appear as the multiplicative factor here, and ln 2 will disappear as a constant. And if you want to find T, right, at the age of that ancient object or the archaeological specimen, you have to throw away everything. Half-life to the left-hand side, ln 2 to the left-hand side, the negative side to the left-hand side. So once you throw away everything except for the variable T, which is our time we want to calculate, we get this one, right? And you put it into the calculator. Actually, you may have to convert the half-life to second, but it's tedious, right, to say the large amount in this second unit, right? It's better just leave the half-life in terms of on the scale of years, and you just simply calculate this one, put it into the calculator. You get the age of that object around, I don't know, 11,500 years before. So yeah, that's the answer from carbon dating. This is the way to determine the age of some objects. Yeah, and we're gonna rely on this. Okay, let's go to other stuff, and yeah, we finished the carbon dating. One difficulty with radiocarbon dating nowadays is that the concentration of the carbon 14 in the atmosphere has varied. Yeah, because what is the reason behind it? Because we have something like we have car, right? We have car, and we use the fossil. We burn the fossil in terms of fuel, in terms of gasoline, in terms of diesel, in terms of other kinds of oil, and yeah, burning fossil fuels means there are more carbon dioxide on Earth, right, in the atmosphere. And once we put more carbon 12 from the fossil, so the ratio between carbon 12 to carbon 14 might have changed already. Okay, so we could not do anything because you still want to travel, right, on Earth, and you need to use the car. So once you burn more fossil, carbon 12 will exit in the air, right? So 1 by 1 million may not be valid anymore for the ratio between carbon 14 and carbon 12, and that's the sad thing, right? Okay, that's the reason from the human uses every day, and another reason is that due to the war, right? They want to build up a better and better weapon, and nuclear weapons is one of the things. Okay, you will see it later. Once you make the experiments around nuclear weapons, you also increase the amount of carbon 12 in the air. So we could not avoid this. Yeah, that happens in nature. Okay, correction can be made on the basis of other data. You may use some other material instead of carbon. You may move to phosphorus. You may move to other elements, okay, apart from carbon, okay, because phosphorus may not have some side effect from the burning fossil. And you just consider any meaningful isotope of the phosphorus, okay, and use the same way to determine the age of an object. Okay, that's the thing. Now we move to the next topic, which is nuclear reactions. This is what the M605 has already parted. Okay, we have seen the decays of unstable nuclei in terms of alpha particle emission, beta particle emission, or even once the nuclei are not stable, we got the gamma ray distribution too, right? Yeah, we could not avoid this. Yes, that's the thing. The next one is what happened to this? I don't know. The camera doesn't focus on the iPads. I don't understand. Okay, it should focus on the iPad. It's just blurred. I don't know how you could see it. Okay, that's the introduction to nuclear reaction process. Nuclear reaction are the changes of nuclear structure. Okay, you have seen the change of nuclei in nature in spontaneous way, right? It happens in nature. Human didn't do anything to that. But for us right now, we are gonna see the results from due to human. Okay, human try to force or to decompose the. I don't know whether I share the screen or not. So maybe I didn't share the screen, right? Oh, I didn't share the screen. I'm sorry for that. ก็ชัยสิทธิ์ก็ไม่ได้เตือนผมเลยนะไม่ได้แชร์จอครับ Okay, yes, okay, the nuclear reaction are the changes of nuclear structure by human. Okay, it's human made in. I don't understand. Okay, it should come. Okay, in the changes of nuclear structure by bombarding them with energetic particles. The first nuclear reaction process took place in 1919 once the Rutherford bombarded nitrogen. Okay, this is the thing. Okay, nitrogen. He bombarded means he put some high-speed object. He tried to hit nitrogen by high-speed object, and that object is alpha particles, right? You have seen at the beginning of the previous chapter, right, in atomic model. Yeah, alpha particle is the nucleus of helium, right? Yes, and nucleus helium is accelerated. Okay, bombarding means the particle is accelerated with high energy, and it moves to the nucleus of nitrogen, and the outcome turns to be oxygen 17 and one proton. Okay, it's the nucleus of hydrogen. Okay, and yeah, that's the thing. This process is known as the first nuclear reaction on Earth. Okay, yeah, we could not do anything. We, on behalf of human, we have to thank Rutherford. And after that, after Rutherford start this process, there are many more scientists of physics try to bombard some nuclei to get something new, right? So once you get something new, you may have chance to obtain the Nobel Prize, or you can get the funding for your research and so on, right? So yeah, that's the first inspiration for a human being to have the nuclear reaction process, nitrogen 14 to oxygen 17. Okay, let's consider one of the nuclear reaction process. The neutron is discovered in 1932, okay, in England. This person, Robert Chadwick, okay, bombarded a beryllium. You know beryllium, right? Beryllium is the fourth element on the periodic table. Let's go to the periodic table. Oh no, we don't take care of it. Oh, we go to this one. Oh no, not this one. Oh, let's go to that. Okay, beryllium, right? Periodic table. Beryllium, right? Periodic table. Okay. Beryllium is here. Okay, beryllium number 4. Okay, number of the number of proton is 4, right? Yeah. Robert Chadwick has the beryllium 94 is the object, and he accelerated the alpha particle, the nucleus of helium-42, to hit the nucleus of the beryllium 94. And once it hits, okay, this one has the kinetic energy, it moves with a high speed, it hits this one, we get carbon 12, and there is another particle which is X, okay, and with atomic with the mass number A, a number of nucleons as A, a number of protons at the variable Z or Z. So the question is, what is the particle XAZ in the reaction of 79? Okay, in order to deliver the answer to this, เราต้องจบที่เท่าไหร่นะ14รู้สึกว่า28นะครับ28อาจารย์ณัฐพงศ์ครับที่เขาเกิดอุบัติเหตุครับเขาจะมาขอเขาเรียกว่าอะไรขอคืนนะครับขอคืนวิชานะครับขอคืนชั่วโมงนะก็ผมก็จะสอนแค่let me check ขออนุญาตเช็คนะระหว่างนี้ก็จะได้แจ้งคุณไปด้วยนะครับจะได้เข้าใจตรงกันนะว่าเดี๋ยววันศุกร์ทำไมผมสอนแค่คาบเดียวนะโอเคท่านอาจารย์ณัฐพงศ์นะที่เขาเกิดอุบัติเหตุนะเขาติดต่อผมมาว่าจะขอชดเชยคือเนื่องจากก่อนนู้นครับผมแทนเขาเนาะwhere is the information I don't know where is that 28 here โอเคนี่นะครับเขาขอเข้าคืนศุกร์ที่28นะครับคาบ2นะครับเราก็จะพบกันแค่คาบ1คาบเดียวนะของคุณนะครับวันศุกร์ที่จะถึงนี้นะครับเราเรียนกันคาบเดียวแล้วก็ปล่อยให้อาจารย์ณัฐพงศ์เขาต่อนะครับ605ต่อไปเลยนะครับโอเคไหมเข้าใจกันตามนี้นะครับแล้วก็ next time is 4th โอเคสัปดาห์ถัดไปด้วยนะครับก็คืนของเราปกติแต่ว่า605คาบ4นะครับก็มีดังนี้นะครับรับทราบไว้ด้วยนะครับโอเคไหมเดี๋ยวคุณจะได้เข้าใจว่าเดี๋ยวทำไมผมนะครับอาจารย์บำรุงหนีไม่สอนคือเขาขอคืนนะครับผมก็ต้องให้คืนเขานะครับคื คือรับผิดชอบให้ช่วงที่เขาบาดเจ็บให้ครับ Okay let's get back to our problem and we're gonna solve this one, right? We have to deliver the information about the x, right? X is usually the unknown variable even in mathematics, also here in physics, right? Okay, what is the element x? In order to find x, we have to know this process, right? The nuclear reaction process is balanced, and in order to make it balanced, the number of nucleons should remain the same, okay, and the number of protons should remain the same, whether at the beginning or after the reaction process, okay. Well, we have to make them balance at the upper row and the lower row, right? 4 plus 9 should be equal to 12 plus a, so we get this equation 80a, right? The number of nucleons should remain the same, right? At before the process and after the process, right? Before the transformation and after the transformation, right? Before the transformation, we have 4 plus 9, which is 13, and we have 12 plus a is unknown. After the transformation, that's the number of nucleons. The number of protons too, right? 2 plus 4 before the transformation, and 6 plus z after the transformation. And you just solve these two equations. It's not beyond your ability in the high school level, right? 4 plus 9 is going to be 13, and you have here 12, right? Which is negative 12, right? A is number 1, and z 2 plus 4 is 6, and we have already 6, that should be 0. So we have the element, number of nucleon is 1, number of proton is 0. What is that? What is that particle? What is the particle that has 1 nucleon and without proton? And that particle will be neutron, right? And this is the time where on Earth the human has discovered the neutron. Okay, Robert Chadwick discovered the neutron from this nuclear reaction. Okay, let's move to the next stuff in the story about nuclear. Oh, I used the wrong mouse. During the nuclear process. Okay. During the nuclear process, we have another quantity that we have to pay attention, which is really meaningful in the rest of this chapter, and that's about is called reaction energy or release energy. It's the quantity that you may have already seen before. Okay. For any reaction process, we have the reactants, okay, the input side, including the element A, nucleus B, and we put some energy, one of them or both of them are moving so that they have kinetic energy, and when they hit each other, they are gonna be transformed into 2 nuclei or even more. Okay, for example, nucleus C, nucleus D, and we want to find the reaction energy. The reaction energy will be defined as the difference of the mass at the input side subtracted by the mass at the output side. Okay, so simply speaking, that's the mass of element A and nucleus A, mass of nucleus B reduced by the mass of nucleus C and mass of nucleus D. And that's the Albert-Einstein relation, right? We call it the mass to energy, EMC², but this is known as the variable Q. Reaction energy is specific for the reaction process, nuclear reaction process here. But anyway, it's based on the EMC² by Albert-Einstein. So this one is C², right? C². And you can also use the simpler version, which is small m of nucleus A, small m of nucleus B, small m of nucleus C, and small m of nucleus D. And it's going to be 931.5 mega electron volt per atomic mass unit, right? M, small m is the mass in atomic mass unit. Oh, all right. The energy can have two possibilities, whether it's positive or negative, right? If the mass at the input side on the left side is greater than the mass on the right hand side, it means the kinetic energy of the resulting particles will be increased. Okay, will increase. So when Q is positive, the total mass decreases. Okay, mass here. There is a mass loss for both particles, and the mass loss just convert itself to become the kinetic energy for both particles. So both particles will have more kinetic energy than the input side, and that's the positive Q case. For the negative Q case, the negative reaction energy, the mass at the output turns to be greater than the mass of the input. And that might happen a little bit too. The total mass increases. Okay, the mass at the right hand side is greater than the mass, the total mass at the left hand side. So the total kinetic energy decreases. Okay, you could remove the object with a high speed here, and the outcome turns to be two new nuclei, but with lower speed, with lower amount of kinetic energy because the mass increases. Okay. The former reaction, the positive Q, okay, the mass at the left hand side or the input side is greater than the mass on the right hand side, is known as exothermic reaction. Okay, this is the physics term, and in chemistry they are gonna say exothermic reaction, or in chemistry term, okay, it means that the mass at the left hand side is greater than the mass on the right hand side after the process. And for the case of negative Q, it's known as the endoergic reactions. Endo means down, right? The mass increases, but the kinetic energy decreases, so it's down, okay, decreases. Endoergic reaction, it's the word in physics. But for the people in chemistry, they are gonna say endothermic reaction. Okay, the kinetic energy at the output decreases. Okay, let's take a look at the one example of nucleus bombardment. We consider lithium-73, right? The lithium is before beryllium. Lithium-73, okay, is the major nucleus, and we accelerate the proton, and we accelerate the proton to have high speed, high kinetic energy, and the proton will hit the nucleus of lithium-73. We get 2 alpha particles, helium-42, right? 2 times. You need to observe that 1 plus 7 is equal to 4 plus 4. That's the number of nucleons. And the number of protons, 1 plus 3 at the left hand side is equal to 2 plus 2 on the right hand side. Okay, 2 alpha particles. Okay, determine the reaction energy Q. What is the Q? The energy that we could get that take place from this process, right? From process 82. So we're gonna use 83 to calculate the amount of the energy from this nuclear reaction. Okay, this is the man-made. Okay, you accelerate proton, doesn't happen in nature. The way to do is we have to follow 83. What is the mass of hydrogen? Okay, you just take the mass of hydrogen, and mass of lithium-73 subtracted by mass of helium, 2 times of alpha particles, so there will be number 2 in front of the last term. And this is the mass in SI system, right? In kilogram. We don't it's not convenient to us. We're going to use the mass in physics, especially in chapter of nuclear physics. We're going to use the mass in atomic mass unit. So you go to the table and pick up the mass of hydrogen nucleus, and you take the mass of lithium-3, which is 7 blah blah blah, and the mass of helium-4, which should be something very close to 4, and it's 4.002603. Okay, and you multiply. Okay, we don't use the straightforward version of the Albert-Einstein equation. We use the converted version at the beginning of this chapter, 931.5. Okay, mega electron volt per unit, and then you make the multiplication. Okay, make the subtraction here first. You get this amount. You multiply it with this factor in the EMC square, and you get 17.35 mega electron volt as the outcome from bombarding lithium by proton. Okay, so what is the meaning to this? What is the meaning? It's not only the calculation from mathematics, and we could not understand anything. You have to also understand what is the fact in this thing. Okay. Yeah. One can the reaction energy is equal to 17.35. So it means after the bombardment, the helium-4 or the two pieces of alpha particle will have more kinetic energy. We will have more total kinetic energy from the input by 17.35 okay mega electron volt, and yeah, the initial total kinetic energy is the energy by proton and lithium nucleus, right? Yeah. Let's consider the next example. Find the reaction energy for the Rutherford experiment. So we need to open the it's 7, right? No. Today is 26. Here 6. Okay. Yes, the Rutherford process is this one, right? No, this one. Okay. He accelerates the alpha particle helium-4 to hit the nucleus of the nitrogen-14, and he got oxygen-17 and a proton, right? So in order to find the reaction energy from this process, we have to apply this formula 83, right? The 83, which is the mass difference times c squared, and we use the simpler version, mass in atomic mass unit, and 931.5 mega electron volt per atomic mass unit, right? Okay, for the Rutherford process, he starts from helium-4 at the alpha particle and the nitrogen-14. So you have to go to the table and pick up the atomic mass of helium-4 and nitrogen-14. Once you get two values, just leave it here. Okay, this is the mass of the helium-4 in atomic mass unit. It's not in kilogram. And the mass of nitrogen-14, you have to go, you just pick up it from the table, and you get the result, which is not exactly 14. Okay, it's you get only exact number for only carbon-12, but not other elements. Okay, nitrogen-14, 14.003074. That's the first two terms on the left-hand side according to equation 82. And the outcome is oxygen-17 and proton, right? We're going to have mass of object C, a mass of object D, a proton, and you get 16.99 and 1.007825. That's the mass of proton. That's the mass of oxygen 17. And you take this, make the subtraction of these four terms. You unfortunately it turns to be negative value. Okay, and yeah, at the end you have to multiply by 931.5 megaton volt per atomic mass unit. Yeah. Anyway, even we get the negative value of the mass difference, the energy will turn to be also negative value, which is minus 1.192 mega electron volt. Okay, it's a little bit negative, but what is the meaning to that? The process by Rutherford is not exergic, it is endoergic. Okay, it brings the decreases the amount of kinetic energy at the output because it's negative value. So 1.192 mega electron volt will be absorbed by both particles, and the kinetic energy here will be less than the kinetic energy at the beginning. So Rutherford reaction will take place if the total initial kinetic is at least 1.192. Okay, you have to accelerate both particles, whether helium-42 or nitrogen-14, so that the summation of both kinetic energies is greater than 1.192. Otherwise, this process will not turn to be true. Okay, this process will not occur because we have to bring also the energy by amount 1.192 mega electron volt to these two particles so that this process could take place. Okay, yeah, that's the thing. The endothermic reactions will not occur unless the incoming particle has at least enough kinetic energy to overcome the energy deficits. Okay, yeah. In order to destroy the nucleus of something like alpha particle is also a very stable nucleus, nitrogen-14 is also a very stable nucleus. You have to put the energy whether to helium-42 alpha particle or to nitrogen-14-7. Okay, and yeah, the kinetic energy will be used to separate or destroy the nucleon. So we get oxygen, so that we can get oxygen and proton like that. Okay. The next one is so we have finished the nuclear reaction, right? The process is made by human. Okay, that's the human-made process. I don't know for which purpose you may wanna get some rays to use in medicine to get rid of the cancer in human body. We can use for that. We could use the theory for that purpose too. Okay, let's go to the next topic, which is nuclear fission. Nuclear fission is a decay process in which unstable nucleus are split into two fragments of comparable mass. So the big nuclei will be decomposed into smaller nuclei. So, okay, not only one nucleus. In such reaction, the total mass of the product is less than the original mass of the heavy nucleus. Okay, this process will take place only when the there is mass difference. Okay, the mass difference is positive. So the mass at the beginning is always greater than the mass at the output. Okay, fission was discovered in 1939. Okay, it's the nuclear reaction took place in 1919 by Rutherford, right? And in 1932, Robert Chadwick discovered neutron, right? Let's observe the timeline. And in 1939, 7 years later, Otto Hahn and Fritz Strassmann, has discovered the nuclear fission. This is the human-made again. Okay, it's not a natural process. It's a human-made. You accelerate the neutron okay, with high energy, with kinetic energy, an amount of kinetic energy to hit the nucleus of the uranium. And you know that uranium has several isotopes, right? 236, 235, 238, 239. 235, uranium 235, 235 is the number of nucleons, is the major isotope that we could use in nuclear fission. So we accelerate neutron to hit the nucleus of uranium 235. We get, we just put neutron into the nucleus, right? We add one nucleon into the nucleus of uranium, and this element becomes 236 uranium, which is the bigger isotope version of uranium 235. But the number of proton will be the same because neutron doesn't change any sort of proton. Okay, uranium 236 with star, what does that mean? It means the nucleus is in the unstable status, so it has some vibration, right? Because you hit the nucleus of uranium 235 with a high speed, a moving neutron, so the whole piece of nucleus of uranium might get vibration and absorb the energy from neutron. But once the time goes by, the uranium 236 will be separated into two nuclei, okay? And those two nuclei could be considered as X and Y, okay? Two different nuclei. And apart from that, we're gonna get also the neutron, okay? You insert the neutron to uranium, and uranium is bigger, turns to be bigger, and after that, because there is vibration, the nucleus are no longer stable. They are gonna separate them from each other, and we get now two new nuclei, nucleus X and nucleus Y, and we have also additional amount of neutron, okay? N is the number of neutrons, okay? X and Y are daughter nucleus from splitting uranium 236 in the vibration mode. Okay, to uranium 236 is only the intermediate state, okay? It doesn't last quite long, okay? This one turns to be this line almost immediately. The time that uranium 236 will last is only 10 to negative 12. And what is that? It's femtometer, right? It's a femtometer. So yeah, that's the thing. It's on the scale of femtometer. Yeah. What else? Let's take a look at the better image. You accelerate the neutron, okay? Neutron approach uranium 235, okay, with 92 proton at the lower subscript. Before the fission here, okay, it's in the excited state. Because of the vibration, the uranium 236 will expand the nucleus in this way. It's kind of liquid drop or water drop, okay? When it's expand more and more, finally they're gonna be cut down the junction here, and the nucleus will turn to be two nuclei, nucleus X and nucleus Y. There are two lighter nuclei and several neutrons, okay? After this one is exploded, this nucleus is exploded, we have the big nuclei. These two X and Y are called daughter nuclei, right? According to this process, X and Y. We will talk about the meaning of X and Y later, but at least you know that the nuclear fission will bring you to two smaller nuclei with relatively comparable mass to each other. And apart from that, we're gonna get some amounts, okay? 2 or 3 neutrons from this process, okay? It depends on the possibility. Okay, this is the nuclear fission which is model as the liquid ผมช้าไปประมาณ6นาทีครับขออนุญาตเลยนิดนึงครับโอเคเดี๋ยวปล่อยคุณนะครับอีก5-6นาทีนะครับwhat else yeah let's get into the detail what are x and y because we didn't say the information about x and y are known as daughter nuclei from splitting uranium to the 6 in the vibration mode right x and y could be taken from this one okay because this happened with a large amount of transformation we could not know one exactly we have to use the probability okay the mass distribution of fission fragments x and y could be the elements with between 90 nucleons to 100 nucleons. This is the highest chance for the first daughter nuclei for the first daughter nucleus and for the second daughter nucleus y okay they say this is x this is y we cannot say it exactly because it has some chance okay to get some other nucleus or nuclei between 132-33 until 143 okay this is the bigger nucleus you can obtain from separating or splitting uranium to the 5 okay and you just go to periodic table or the table by physicists in order to find which element that has 140 nucleons that has 95 nucleons okay and one of the most taken place process is this one okay we accelerate neutron to hit the uranium-235 and the uranium-235 will be uranium-236 with the vibration with the in the excited state yes as I told you the chance for x and y is in between this column okay because this is the highest chance you just pick up and one of the thing is 92 okay 92 is between 90 and 100 and that element is krypton okay krypton of 36 protons and the element y would have the number of nucleons between 133 34 to 143 44 and that one is 141 right 141 nucleon and the number of proton is 56 that element is barium okay x and y could not be explicitly said it depends on the chance in this graph in this plot okay and apart from that as I told you we have n times neutrons right we get 3 neutrons from this process okay from barium and krypton barium and krypton are fission fragment okay and most reactor in nature most reactor that operates nowadays in the world makes use of uranium as fuel okay you may know that uranium is the major fuel for nuclear power plant okay that's the most popular element to us okay now it's 14:06 it's time to let you go right today is Wednesday so we don't have homework right but next time on Friday we're gonna have homework okay if you have any questions just let me know if not then we're gonna stop our lecture right now okay ถ้ามีคำถามนะครับโปรดถามได้นะครับสัปดาห์หน้าเราเจอกันเฉพาะคาบแรกเท่านั้นนะครับเพราะว่าคาบ2นะครับอาจารย์ณัฐพงศ์เขาจะขอชดเชยคืนนะครับโอเค see you next time สวัสดีครับบ๊ายบายครับโอ้โห That's the better version. Okay. Okay, all right. Okay. Okay. Some of the Yes, 1, 2, 3. Oh my god. DOBS has some problem in microphone, right? Oh, you didn't open this one. Oh my god. You forget to open the microphone, right? Hello. Actually, yeah, this one is Shure MV. Oh, you forget to turn on also the microphone here. In this one, okay, works fine. Oh, we forget all the time the microphone. Yes. Okay. Yes, poor. Now we have to stop. We have to stop the video here, right? We have to stop stop the mic of the video to okay. It's there in Gina Pub. Cup. No. Papa with. Okay. The video bitrate is somehow so you can use this right. Power with twin shot win. Power with twin shot win. Okay. ก็ฝั่งนี้ก็สิดิใครไม่รู้ wait so that's this is the to take a look at this. Okay, the buttoning, buttoning. Let's see this forward. Okay, it's 04. Try to teach this 604 today. It's in the for us in this one here, but we're gonna have this. Yes. Super sim. Okay. Three places. And yes, we forgot to turn on the microphone. Video bitrate to be high, then it's video bitrate. Yes. Well, I have to open the Steam. Right here. Yeah. And the Safari is this one. We're gonna move it to that's the we have to switch account to this one. Right. And let's see what's going on with your channel. And now this one, right? Right, seeing this one to look at white version of the to look at the go live version of the Streamlabs. To right, yeah, I go to the live version of Streamlabs 2 and no, go to this account.ลืมเปิดไมค์ right, we go to the Streamlabs version, or even the Zoom version. Right? The Zoom has no sound. Here Streamlabs. No, it's not made for key. Okay, it's not made for key. And that's the what is that? So where is it? Right. Okay. But my you need to try. Right, okay. Excellent. So, okay, anyone is watching. Okay, from 605 you have already right. We have now Thanagon, right? Thanagon had the OBS number 1 to OBS number 1 and สุภวิทย์นะครับพระสิทธิ์นะครับเหล่าศรีเมืองครับ and nothing more, right? No one more. Yes, one thing นนทกรด้วยนะครับนนทกร okay, one thing I need to inform you is the following นะครับมีบางสิ่งที่ผมจะต้องเรียนแจ้งคุณก่อนนะครับสิ่งที่จะต้องเรียนแจ้งคุณก่อนก็ดังต่อไปนี้นะครับright that here okay นะครับก็ขอเรียนแจ้ง M605 นะครับ605นะครับก็คือว่าวันศุกร์ที่จะถึงนี้เนี่ย28วันนี้26นะครับเพื่อนมาถึงแล้วหรือยังนะปนทัศน์นะครับปนทัศน์ด้วยนะครับที่ OBS นะครับทุกคนโอ้โหไม่ขอเก็บชื่อชัยสิทธิ์ห้อง604ไปก่อนนะส่งให้เขาไปก่อนโอเค604 M604 what is that here ส่งโดนลืมนะครับโอเคก็เรียนแจ้งคุณก่อนนะครับสำหรับห้อง605นะมีปานทัศน์พิมพ์มานะครับก็ไม่รู้มาครบกันหรือยังนะครับวชิรวิทย์ก็พิมพ์มาแล้วด้วยนะครับคือนะครับต้องเรียนแจ้งคุณว่าวันศุกร์ที่28นะครับก็เราจะไม่ได้พบกันนะไม่ได้พบกันหมายถึงว่าผมไม่รับผิดชอบนะครับหมายถึงว่าคุณครูหรือท่านอาจารย์ณัฐพงศ์นะครับที่สอนน่าจะเป็นเลขวิชาเลขคุณนะครับเขาจะขอคืนนะครับก็คาบที่3คาบที่4ตอนรู้สึกจะเป็น10ถึง11:50เนาะของคุณนะครับเขาจะขอคืนนะครับดังนั้นเราจะไม่ได้พบกันนะครับทุกคนรับทราบนะครับโอเคไหม605นะครับโปรดรับทราบนะว่าเราจะไม่ได้พบกันวันศุกร์นะครับดังนั้นวันนี้เราจะเรียน2คาบแล้วก็น่าจะวลินทรด้วยนะครับน่าจะสั่งกันบ้านเลยนะครับแล้วก็ไม่สั่งดิเพราะว่า604เขาจะต้องอีกครั้งหนึ่งเนาะคุณไม่ต้องมีกันบ้านในอาทิตย์นี้เนาะแล้วก็604เขาจะเริ่มคาบนู้นเลยนะครับคาบที่2เลยนะครับคือผมจะสอนแค่เฉพาะคาบแรกของวันศุกร์นี้เท่านั้นโอเคก็นั่นคือ28นะครับครั้งแรกนะที่มีการเปลี่ยนแปลงครั้งที่2ก็จะเป็นตรงนี้นะครับ605คาบ4นะครับหมายความว่าคาบที่2ของเราอาทิตย์หน้าวันศุกร์หน้านะก็ผมก็จะสอนแค่คาบเดียวแล้วก็อาจารย์ณัฐพงศ์เขาก็จะขอคืนนะครับโอเคไหมวลินพวัตรรับทราบไปด้วยนะครับบอกเพื่อนนะตามนี้นะครับอัดวิดีโอไว้ให้แล้วนะคุณก็รับทราบกันไปนะครับwhat else nothing more right ก็จะประมาณนี้หากมีข้อสงสัยใดนะครับไม่ท้วงติงกันได้นะครับว่าผมทำผิดทำถูกสิ่งใดนะครับโอเคก็จะประมาณนี้นะครับโอเคlet's get back to our lesson. This is the M604, right? We're gonna open a new file. Put here. This one. It's gonna be called. What is this? Okay, copy. Copy this. This one. M605. Okay, so this one and open also here for you M605 M60526 this one. Okay, you have reached so many topics before I hit M604 because you don't have any trouble in electric setting or online classroom setting. The M604 suffers a lot from the missing time during setting. Okay, M605. Why should I? Okay, I have to go to your classroom, right? 6. Oh no, the same file. 605.26. This one. Okay, in yeah, to go. Yes. If I can remember, we would arrive at this one, right? The power plant. Let me check it again in the classroom. นะครับห้อง605นะครับผมแจ้งไปแล้วนะว่าวันศุกร์นะครับเราจะไม่ได้พบกันนะเนื่องจากว่าอาจารย์ณัฐพงศ์เขาขอชดเชยนะครับผมไม่ได้เรียกร้องอะไรนะเขาพร้อมกลับมาคืนนะครับก็ผมก็ให้เขาคืนทันทีเพราะว่าแค่ช่วยเหลือการในยามที่เขาบาดเจ็บแค่นั้นเองนะครับเขารักษาตัวยังไม่พร้อมอะไรอย่างนี้ครับ Okay, let me check where did we arrive last time เรา nuclear reaction โอเคไหมครับเรา nuclear reaction โอ้คุณก็จะนำ604แค่นิดเดียวสิเนาะ right เราก็นำคุณก็จะนำ604แค่นิดเดียวyes รูปนี้หลังรูปนี้ครับโอเคนี่คือของเก่าของเราครับโอเคso good afternoon everybody, welcome you to SCI33206, which is the last person in OS number 1 channel, right? And for the people in Streamlabs, you are Panatron, right? Number 2, no one in Zoom 2 channel, right? Okay หาเอาเองนะครับมี4ช่องนะครับผมบอดคาสต์ไลฟ์อยู่ตอนนี้4ช่องครับใน YouTube นะครับคุณหาเอาเองนะครับกดคำว่า SCI นะครับ33206แล้วก็วันเนี้ย January 26 นะครับจะมีอยู่4 channel นะครับใน YouTube นะครับเลือกเอาอันไหนนะครับที่สัญญาณดีเพราะว่า604ที่ผ่านมาผมลืมเปิดไมโครโฟนโอ้ก็อยู่กันได้ก็ไม่แจ้งนะว่าแบบใน Zoom ก็ลืมแชร์หน้าจอนะครับก็ไม่แจ้งกันครับโอเค anyway ดีเนี่ยพยายามเปิดเครื่องหลายๆเครื่องเพื่อว่าเช็คสัญญาณนะว่ามันออกดีไม่ดีนะครับมันก็ลืมจนได้นะโอเค Okay, fission reactions are always exergic. Okay, it means the mass difference is positive, right? And because the fission fragments have greater binding energy, you know, the unstable nuclei that has not so good energy binding the nucleons turns to be a smaller nuclei, turn to be two smaller nuclei, daughter nuclei, let's say, and in those smaller nuclei, they have better binding energy per nucleon, so they are more stable than the initial nucleus like uranium-235 and so on, right? So the fission fragment have greater binding energy per nucleon than the original nucleus for that reason. And the total kinetic energy of the fission fragment is enormous, so it means it's very big. The outcome energy, okay, you know, for producing electricity or for making the nuclear weapon, nuclear bomb and so on. Yeah, the people use this nature, the high energy caused by nuclear reaction process, and it's around 200 mega electron volt Okay, and yeah, it's very very dense energy. You know, the densest form of energy is hidden in terms of mass. Okay, not in fossil, not in electricity. It's in terms of mass, and yeah, the amount of energy released by the fission of a single heavy radioactive atom is around 100 million times the energy caused by the combustion of one molecule in the gasoline engine. Okay, you know, we use gasoline engine for driving the car, right? And yeah, fossil seems to be a very very dense piece of energy, right? But the mass is more dense than that. Okay, in what you could see is the energy by the friction process is 100 million. Okay, I don't know, 10 to 8 times higher than the amount of energy by fossil in the internal combustion engine car. Okay, yeah, you could see the scale, the more sophisticated, the higher level of energy packaged by the fission energy process. And now it's time for us in physics to compute something, right? Yes. If the disintegration energy Q per event is 208, okay, it's almost the same as 200 as said in this sentence, 208, right? It's quite close to this one. It depends on which process and some other factors, okay, and yeah. It's taken from book number 1, example 30.1. Okay, if the disintegrated energy Q is 208 mega electron volts per process, okay, per decay, and per reaction, you can see. Calculate the total energy released by uranium 235. Let's say the isotope 235 uranium of 1 kilogram. Okay, of 1 kilogram, and what is the total amount of energy released by uranium 235? This one. Okay, so how could we determine the total energy? So we have to find the number of nucleon or the number of atoms of uranium by 1 kilogram. Okay, you need to know the number of atoms, which is equivalent to the number of nuclei, okay, by 1 kilogram of uranium, and then you multiply that mass with 931. Oh no, by this one, by you multiply the number of nuclei by this number, because this is the disintegration energy per nuclei per when you make the division of these two numbers, you get 2.5626 10 to 24 nuclei per kilogram. Okay, so this is the number of nuclei by uranium 235 per 1 kilogram. Okay, yeah, we have already got this. Okay, next one is that we're gonna convert the number of nuclei in 1 kilogram for uranium 235 to be energy, okay, by multiplying this number with this amount of energy, mega electron volt per reaction or per nuclei. So 208 mega electron volt per nuclei times this number nuclei per kilogram. We're gonna get the energy. Okay, just make the multiplication, simple multiplication. We get 5.3301 10 to 26 mega electron volt per kilogram. Okay, it's the total energy caused by 1 kilogram of the uranium 235 isotope. Okay, and the next question is that how many kilogram of uranium 235 would be needed to satisfy the world's annual energy consumption. Let's say this is the amount of energy that the people around the world will consume per year. Okay, in 1 year, let's say if the number of population stay constant, but actually it's not the case because we use more and more energy every year, right? So if this amount is constant, remains constant for every year, so what is the total amount of uranium we need to supply this energy consumption, energy need, which is 4 times 10 to 20 joule. Okay, that's the SI unit, right, for the energy. But for us in nuclear physics, we compute the energy, we observe the energy in terms of mega electron volt, which is the SI version divided by the electron charge value, right? Okay, this is the amount of energy we could get from 1 kilogram of 1 kilogram of uranium-235. We're gonna compare it to the energy that is required by human around the world, okay, all over the world. So number of kilogram that we need will be the ratio between the desired amount of energy around the world by the amount of energy we could get from 1 kilogram of uranium. Okay, whether in terms of joule or mega electron volt, we're gonna convert it later. Okay, yes, 200 4 times 10 to 20 joule as the numerator, nothing more, right? And we wanna convert mega electron volt to be joule, okay, so that the joule can cancel each other at the numerator and at the denominator, right? So we will convert this one, and what we could do is what is the amount of joule per mega electron volt? Yeah, 1 joule per electron volt is 1.6 times 10 to negative 19, right? But once we observe it per mega electron volt, we're gonna multiply it by 1 million, right? 10 to 6, right? So 10 raised to 6. So 10 to negative 19 multiplied 10 to 6, which is million, is going to be 10 to negative 13 only here, okay? And after that, you make the multiplication and you make the division here. And it turns out that the number of kilogram of the number of uranium in kilogram will be 4.6845 million kilogram, okay? And that's the amount of uranium we need to supply the energy for the people around the world without any other energy sources, okay? ปิรทัศน์มานะครับที่ธนทรนะครับก็กดชมวัดนะครับก็บอก605นิดนึงครับว่าวันศุกร์นี้นะครับเขาจะชดเชยนะเราไม่ได้พบกันนะครับแล้วก็วันนี้ก็คงไม่สั่งการบ้านด้วยนะครับเพราะว่าต้องให้604เขากระดึบขึ้นมานะครับจำนวนการบ้านเท่ากับคุณครับ alright yes that's the number of kilogram, right? It's mega kilogram, okay? I don't know, 1 ton, 1,000 ton, 4,684.5 ton per year, okay? That's the amount of uranium we need to supply the total energy required on Earth, okay, around the world. Now let's move to the next example. Next example, we talk about fission again. Okay, in the same way, it's a fission by uranium, maybe uranium-235, the same thing. Okay, let's say if the fission process or the nuclear fission reaction, would give you 200 mega electron volt per process per reaction. Okay, once you decompose one nucleus of uranium-235, you will get the energy around 200 mega electron volts. And how much uranium has to undergo fission per unit time to provide 3,000 megawatt of thermal power. So this is again the amount of energy. It's not energy, it's power, right? Because watt means joule per second. It's the unit of the power. It's not energy, but it's energy per time, right? So this one is equivalent to 3,000 million is 3 times 10 to 9, right? 3 times 10 to 9 joule per second is watt, right? And yeah, let's say each process would give you 200 mega electron volts. Okay, we're gonna convert this one to SI and we make cancellation. We can get the number of we can get the amount of uranium. Okay, now from 89, the number of nuclei for uranium-235 per kilogram is this one, this number, right? 2562, right? 25626 and 10 to 24. Okay, very large amount. That's the number of nuclei we could get from 1 kilogram. And yes, the number or the amount of uranium in terms of kilogram per second will be the required power, the power required by somewhere, right? By some places. 3 times 10 to 9, okay, 3,000 megawatt. So it's equivalent to 3 times 10 to 9 joule per second. Okay, that's the decided amount of energy, power. And after that, we use the number of uranium-235 nuclei per kilogram times the amount of released energy, from the fission process. Okay, and they say instead of 208, okay, they say 200 exactly. So we're gonna use N, right, which is the number of nuclei per 1 kilogram. Okay, it's 2.5626 10 to 24, and Q is the mega electron volt, the energy per nuclei, right? So yeah, you will get the amount of nuclei per kilogram. You get the energy release per nuclei, and after that you make the multiplication of these two numbers and you divide the desired amount of power by this product, and you get 3.6539 10 to negative 5 kilogram per second. Okay, you please note that mega electron volt will cancel each other and joule will cancel each other here. So we move kilogram above and second will stay behind, underneath. So we get kilogram per second as a unit for this quantity, which is the decided variable here, number of kilogram per second. We need 3.6 10 to negative 5. It's not easily understandable, right? 10 to negative 5 kilograms. So we convert this one to okay, this 10 to 3, right? So it's negative 2. Negative 2 means if we go further, we're gonna have 36, right? 36.539 milligram per second. So in order to supply the power of 3,000 megawatt, we have to burn or to decompose the uranium-235 isotope by 36.539 milligram per second. Okay, it's the amount of burning uranium per second. Okay, it's not the exact amount of uranium only. Okay, it's rate of burning, or let the uranium be in the fission process per time. All right, that's the nuclear fission. Okay, there are two examples to compute regarding the energy requirement. And before that, we have calculated the reaction energy, right? The mass difference times 931.5 mega electron volt per atomic mass unit. Okay, now we finished already nuclear reaction. We finished the nuclear fission, and we are going to start the nuclear fusion here, this section. Okay, this topic. Okay, fission is the process of decomposing big nuclei to smaller nuclei, right? ก่อนใช่6.5 Okay, now let's talk about the opposite way. Okay, before that, the big nuclei is decomposed into smaller two daughter nuclei, right? Into two smaller daughter nuclei. In here, it's in the opposite way. Nuclear fusion. Okay, and this one is actually more powerful than the nuclear fission. Nuclear fusion is another reaction process. It's in the opposite way to nuclear fission. Okay, nuclear fusion means we combine two smaller nucleus, two or more smaller nuclei to be one bigger nucleus, or even more. Okay, not only one, not only a single nucleus, maybe two nuclei. Okay, in a nuclear fusion reaction, two or more small light nuclei combine to form a large nucleus. Okay, that's the general form of nuclear fission. We will go into the detail later. When two or more light nucleus combine to form a heavier nucleus, the process is called nuclear fusion, which is the topic here. Okay, we combine two light nuclei into a heavier nucleus. Okay, and after the process, we got also the energy, and this type of process is called fusion. Okay, nuclear fusion. It means the process that fuses some nuclei. Okay, nuclear. Usually, the mass of the final nucleus is less than the sum of the masses of the original nucleus. So this is a good thing, because the mass difference will be the mass difference will be connect the mass difference will be Streamlabs ก่อนอยู่นะครับ Streamlabs ก่อนอยู่พิรทัศน์อยู่ไม่รู้ว่าดูกันได้หรือเปล่านะครับ anyway let's check the stream here of the Streamlabs แล้วพี่พลไปที่ Streamlabs excellent อยู่นะก็อินเทอร์เน็ตน่าจะวิ่งดีอยู่นะครับก็ไม่มีใครท้วงติงอะไรมาผมก็ต้องสังเกตเอาเองนะครับว่าแต่ที่ขึ้น watch เนี่ยก็คือไม่ค่อยมีคนดูเท่าไหร่นะมีคนดูคน2คนหรือตัวผมเองผมก็ไม่รู้นะว่าใครเป็นคนที่ดูนะครับโอเคyes let's go ahead with that usually the mass of the final nucleus is less than the sum of the masses of the original nucleus. It means that let me write down something. This is the mass of the reactants, right? Mass of two things. Okay, and you get a bigger nucleus at the output. Usually the mass here is less than the mass, less than the sum of the masses of the original nuclei. So the mass difference will be positive, right? Because the summation of this one is greater than this one. And the mass difference will be converted to the energy according to the Einstein EMC square formula, right? Yes, we go ahead. The most prominent nuclear fusion reaction is the one that take place in the sun and other star like the sun. 3 examples of the energy liberating fusion reaction are in the following sequence. Okay, this is the sequential reaction process. Okay, it's a set of reaction processes. Okay, not only a single process like in the nuclear fission, right? In nuclear fission, you just decomposed. Okay, it's a series actually. You just decompose uranium, okay, to be smaller nucleus, and the output, which is neutron, right? Which are neutrons. The neutron will decompose another uranium or other material, so that the whole nuclear fission will take place automatically or continuously. But nuclear fission is different. It's a series of a reaction process, not only a single decomposition like uranium 235 to become barium and krypton. Okay, nuclear fission is a little bit more complicated because it contains a series, not only a single fusion reaction, okay, but 3 or 4 reactions that took place together. Okay, and the process like here in the sun, okay, is not the one that took place in fusion. There are many more types of nuclear fusion reactions, but due to the time limit, okay, for us in the high school level, we will not consider all of that. Okay, you have to go to the bachelor degree, okay, and study physics. Okay, you will see more or complete process about nuclear fusion. Okay, the first process in the energy liberating fusion, like in the sun, is the following. 2 protons. When the proton is denoted by 11p, right? P11 and H11 on the left. 2 protons combine to form a deuteron. Okay, deuteron here, and a positron. And positron, right? It's similar to electron. It has the same mass, same spin number, but the charge is different. And positron is not easily stable, right? Usually it's gonna combine. Combine with electron to make the gamma ray or the photon and so on, right? We cannot find positron easily. So 2 protons combine to form, okay, the proton combine together to get deuteron, okay, a bigger version of hydrogen or the proton, right? Which is the bigger isotope of the hydrogen, right? Deuteron, D21. And another product is the positron, right? We get positron from this process too. In of course the electron neutrino. It's like it looks like a beta plus decay. Okay, you start the hydrogen, okay, the proton with another hydrogen, okay, and you get deuteron, okay, which is a bigger isotope of hydrogen. Yes, it's time to observe the reaction energy, right? Yeah, but most of them say fusion process would have less mass at the output, okay, as the output. Okay, this is these two things. The hydrogen's nuclei are the input. So we need to compute the mass of these two nuclei. So it's 2 times the mass of hydrogen 1, right? It's proton, but you should not use the mass of the proton. Okay, this is actually the mass of complete hydrogen. Okay, together with electron, because the mass without electron would be only the mass of proton. Okay, yeah, 2 times the mass of hydrogen, right? 2 times the mass of the hydrogen, because we have 2 pieces of hydrogen here, and reduced or subtracted by the deuteron, the mass of the deuteron 2,1, and the proton 0,1. Okay, proton has no nucleon. Proton is 1 charge equal to the proton, so it's 0,1. Okay, yes, what else? Yes, the mass difference. Okay, and the next one is the mass of the deuteron, right? You just go to the table like this. Okay, you just go to the table. Where is deuteron? Okay, mass of deuteron is 0.014101, which is this one. Okay, and subtraction. And the mass of the proton, right? Mass of proton is equal to the mass of electron. Okay, don't worry about it. Mass of electron, where is that? Here. Mass of electron is 0.000548. Okay, simply speaking, 549. Okay, you make subtraction of these 3 quantities and you multiply it with 931.5 megaelectron volt per atomic mass unit. You get the total amount of energy, which is less than 1 megaelectron volt. It's 0.9315 megaelectron volt. Okay, that's the first process. But it's not the ending story, because once you get positron, this one, this particle is really unstable. Okay, they are really active to other particle because it has positive charge, right? Yes, the positron will annihilate. The positron will combine with an electron in the environment. Okay, around there, wherever whoever has electron, okay, positron will combine with that electron to form 2 gamma rays like this. Okay, proton plus electron is going to be deuteron plus positron, and of course we add the electron, right? Yeah. And here is electron neutrino. The positron and the electron will combine themselves to form 2 gamma. Okay, gamma rays, okay, or photon, right? Gamma is a kind of photon. And if you want to consider the energy from this process, you just find the mass difference between the input side and the output side. Okay, and what is the input then? Input in equation 95 is 2 pieces of proton and 1 piece of electron, right? So we're gonna use this one as the initial on the left hand side, which is positive, right? 2 masses of proton or hydrogen 1 plus the mass of electron. Okay, so 1 piece of hydrogen 1. Okay, 1 piece of hydrogen. Hydrogen 1 is 1.00825. This one, and 2 pieces means we have to multiply by 2. And next is the mass of the electron, right? Mass of electron is provided here, which is a very tiny amount. Okay, 0.00548. Okay, it's 0.00549 approximately. Okay, and subtracted by the mass of the deuteron. Okay, deuteron on the right hand side. We don't take into account mass of photon and the mass of electron neutrino or the electron neutrino. because electron neutrino has the mass even much smaller, 1 by 10,000. Okay, mass of electron. Okay, it's even less than that. So we don't take into account the mass of photon and electron neutrino because the value is not known right now. We just make the subtract to mass of deuteron, and we go to the table to pick up the mass of the deuteron. Deuteron means 1 proton, 1 neutron, right? Deuteron is here, so it's 2.014101, which is this number. Okay, then you make the summation and subtraction, but you multiply it again by 931.5 megaelectron per atomic mass unit. And after that, you will get the outcome as the plain number, which is 1.9543. Okay, this energy will be allocated to maybe to neutrino, to photon, and so on. Okay, our proton, the second process in this series is that once you get deuteron as the output in the previous process, okay, you could see that we got deuteron, right? You just start from hydrogen, you get deuteron. And here, once you have one piece of deuteron, but the initial nucleus you have is hydrogen. You know, the sun is full of hydrogen. Okay, the first 2 hydrogen combine to form deuteron, and the deuteron stay still there. Okay, still stay there. Deuteron will be combined to another proton or the hydrogen nucleus, and it's going to be, okay, you know, the number of nucleus or a number of nucleons is 1 plus 2, so we get 3 here. And the number of proton by hydrogen and 1 proton by deuteron will be 2 protons, and this is equivalent to helium atom, right? So we get the helium-32. Okay, it's not alpha particle because the alpha particle would be helium-42, right? But this one is helium-32. We would say helium-32 as the light version of the helium. Okay, this is the light isotope of helium. It's not helium-42. Okay, helium-42 is very, very, very stable. Okay, and yeah, now from equation 97, we are gonna find the mass difference and multiply it with 931.5. Okay, because we want to convert the mass difference to the reaction energy or the fusion reaction energy. Okay, yes, we start from the mass of the proton, 1.007825 here. Okay, 1.007825. Our next term is the mass of the deuteron. Okay, the bigger hydrogen nucleus, 1 neutron is added. It's 2.014 atomic mass unit. Okay, that's the second particle. At the output, it should be negative, right? The output, helium-32. Helium-32 is this one, okay, 3.016, 0 to 9, okay, you get this summation and subtraction. And you multiply it with 931, okay, according to the Albert-Einstein relation. We're going to convert the mass to the energy, right, EMC squared. But this is the simple version. We multiply it with 931, we get 5.49 megaelectron-volt. Okay, yeah, you start from hydrogen and hydrogen, you get deuteron, you start from hydrogen and the obtained deuteron, you get helium-32. In the last process, there are 2 ways. Okay, there are 2 ways in the third process. Okay, the first one is that the proton, okay, the proton H11 and the light nucleus combine to form ordinary helium-42 and the positron and gamma. Okay, again, at the moment you get deuteron, you get helium-32. Okay, the nucleus is bigger and bigger. And once you combine it with hydrogen, it's going to be helium-42, right? We don't pick up proton here. Proton turns to be positron. Okay, beta CO1. And now we compute the reaction energy, which is the mass of this one. Okay, mass of proton. Okay, mass proton is provided here 1.007825. Okay, this one 1.007825. That's the mass of proton. Now is plus the mass of helium-32, the light helium. Helium-32 would have atomic mass 3.01, 6029. Okay, 6029, this one. And the outcome is the alpha particle, right, or the helium-42. So we need to go to helium-42, which is 0.00263. Okay, that's the mass of the helium-42, the typical helium version. And next one is the mass of the positron. Mass of positron will be equal to the mass of electron, right? So yeah, we get the mass of electron right here. And after that, we make subtraction and summation. We multiply it by 931. We get 19.284 mega electron volt. Okay, 19.284 mega electron volt. That's the mass from the first possible process in the third process. Let's consider an alternative process in the third, in the last process of the sun. This is what the physicists predict. Okay, I'm not sure how they could validate this result. Okay, in the second process for the third process, we don't take proton into account anymore. We just assume that the helium-32, which is the light helium, has exists also somewhere there. So we're gonna add only helium-32 to become helium-42 and two pieces of proton or hydrogen nucleus. And based on 101, we could again compute the reaction energy. Okay, 2 times of the mass of the helium-32 minus or subtracted by the mass of helium-42 and the mass of 2 times mass of proton. Okay, you just take the value from the table, leave it right here. Okay, mass of helium-32 is 3.016029 and mass of helium-42, right, it's going to be there. You just pick up 4.002603. Okay, that's the mass of helium-42 and the mass of hydrogen, okay, which is this one, 0.007825. After that, you make summation, subtraction, blah blah blah, and you multiply it with 931.5. You get the amount of energy from the second process in the third process of the sun. Okay. The above 3 sequential process is known as proton-proton cycle, which is believed to be the status of the energy liberation in the sun and other stars that is full of, that contains a lot of hydrogen atom. Okay, and if it is completely understandable, let's take a look at this figure. Okay, you start from proton, and you get deuteron, right? You get deuteron, and apart from that, we have also positron and electron neutrino, okay, which is a very, very small object or a particle, and it has no charge at all. Okay, next one. Once we got helium, deuteron, right? Deuteron will combine with hydrogen to express the gamma or the photon, and now we arrive at helium-32. Okay, that's the left branch. For the right branch, we start in the same way. Okay, hydrogen and hydrogen. It can be called also protium. Okay, some books may say protium, which means proton, but it's in the same sense as hydrogen, so it's called protium or hydrogen 1,1. Okay, hydrogen 1,1 combine to each other to get electron neutrino and the positron and electron neutrino, right? In here we have deuteron. Okay, deuteron will be combined with protium or hydrogen 1,1. We get gamma ray and helium-32, okay, which is the light version of the helium-42. And in order to be stable, they will combine with each other and they would stay like helium-42, okay. The light helium will combine to each other and we get the typical helium-42. Okay, this is helium-32. And apart from that, we get also proton, okay, 2 protons from this process. It's 3.21, okay, helium-32 to become proton plus proton or hydrogen 1,1 nucleus. Okay, as seen from the reactions, the liberated energy is carried primarily by gamma rays. Okay. Oh no. Oh, no. Where is that? No. Here. Right. Okay. The outcome you could see from this figure is electron neutrino, right? And what else? Electron. Positron, right? This one. Positron, electron neutrino. Okay. And what is this? This is gamma ray. Right, so the outcome would be gamma rays, gamma, and positron beta plus positron, right? This one, and neutrino, right, which is the new variable here. The gamma rays will be soon absorbed by the dense gas, and it will raise the temperature of the dense gas. The positron will combine with electron to produce gamma rays, which in turn are also absorbed by gas within few centimeter. Okay, it could not escape so much. Okay, the gas around there will absorb the gamma ray or the photon. And the important thing is the neutrino. Neutrino will never act or interact with other matters, so it carry around 2% of that generated energy to somewhere else. Even we live here on Earth, there are many neutrinos from the sun, okay, that are moving to us on Earth, okay, because the neutrino doesn't act or interact with any matter. The energy liberating fusion reactions are called thermonuclear fusion reactions. So this one, okay, it's increase also the temperature. So the net energy released, could be calculated from the mass balance, and it turns to be 26.7. Okay, if you add everything, it's going to be 26.7. okay, this one, okay, you get 26.7 mega electron volts from the whole process here. And if the sun were to continue to radiate at present rate or around 130,000 kilowatt hour, okay, that's the amount of power energy that the sun deliver. Okay, if there is a burning process that will deliver energy like 130,000 kilowatt hour. Okay, so our Earth, or the time that will let the sun completely disappear, will be 75 billion years. Okay, we still have time for 75 billion years, and the sun will stop working. Okay, to give the nuclear enough kinetic energy. The fundamental challenge of nuclear fusion is that we have to give the nuclei enough kinetic energy. What is the reason behind it? Because the nuclei will fuse to each other once they are very, very close to each other, and in order to bring such tiny particle to be close to each other, we need a lot of energy, and it should be in a very, very high temperature environment, so that there will be very high kinetic energy amount. Okay, because in nuclei there are some protons, right? And protons are positive charge. Of course, plus or positive charge and positive charge will have Coulomb force. That is the repulsive, right? Pushing force to each other, and but you need to bring the nuclei to be very, very close to each other so that they can interact and will build up a new nuclei for you, right? That's the thing we want. And for two nuclei to fuse, they must come together to within the range of the nuclear force. And the nuclear force in the previous chapter, right? Nuclear force is in the range of 2 femtometer. Okay, so you need to leave two nuclei to be close, like 2 femtometer, which is 2 times 10 negative 15. Okay, which is very, very close to each other. But for us, it's already the same point, right? But it's not the case for the nucleon because they are in a very, very tiny scale. Okay, at the distance of 2 femtometer, we need to put the potential energy for those two protons. And the energy will be on the order of 1.1 10 to negative 13 joule, or 0.7 mega electron volts. Okay, we would get the energy like 0.7 mega electron volt. It's considerable amount, right? It's not like in June you have 10 to negative 13. It's very hard for human to understand. Okay, the temperature T for a gas with the average translational kinetic energy from the Boltzmann formula will be 3/2 times K. Okay, K is the Boltzmann constant. Okay, maybe you have ever heard it. The Boltzmann constant, and we convert the translational energy to become the potential energy, and the temperature to get this amount of energy, it should be 5 times 10 to 9. So what is that? 5,000 million Kelvin. Okay, you have to build up a laboratory with that could support the temperature of 5,000 million Kelvin. Okay, so that the nucleus will be the nuclei will be close to each other, and the nuclear fusion could take place. All right. Yeah, temperature must be on the order of millions of kelvins, as you can see here, 5,000. So that the nuclei are to have enough kinetic energy to survive the electrically powered, proton and proton will push each other, okay? And you need to have you need to have sufficient amount of energy, of kinetic energy. And in order to do that, you need to be in the environment of 5,000 Kelvin, very, very, very hot, okay? Fusion reactions that appear most promising involve the deuterium-2 and the tritium. Okay, this is the expected fusion reaction process that human would like to use for like for making the electricity and so on, for any other kind of energy consumption. Okay, you just start from 2 pieces of deuterium, okay, and of course 4 nucleon, 2 proton, right? And this one is helium-32, okay, and this one is neutron, right? So let's compute the energy reaction, the reaction energy from this process, right? It's in the same way. You have to find the mass difference. The left hand side is positive, the right hand side or the output will be negative, right? So this is the mass of the deuteron. Okay, let's go to the atomic mass table. Atomic mass table. Okay, here. Atomic mass table. Here is deuteron, right? Deuteron has the mass, atomic mass is 2.014101, yes, times 2. And minus helium-32, so helium-32 means 3.016029. Okay, this one, helium-32. And mass of neutron is over there, prepared already here. 1.008665. Okay, almost the same. And you just find the subtraction, and you have here 9314.5 for multiplication, and finally you get 3.2677 mega electron volts. Okay, and another kind of process starting from deuterium is the following. Instead of helium-32, the 2 deuteron may provide tritium. Okay, tritium is a bigger isotope of hydrogen than the hydrogen 1 or the proton or the deuterium. Tritium is bigger than deuterium, but they don't provide the atomic mass of tritium here. Okay, and of course, apart from tritium, we're gonna have a proton or hydrogen nucleus right there. Mass of deuteron is here 2 times 2.014101, and mass of tritium, right? Tritium is the bigger isotope of hydrogen. Okay, and the next one is the mass of hydrogen. Okay, we take this value 1.007825. Okay, we make the subtraction and we get multiplication. We end up with 4.0315 mega electron volts. Okay, that's the process starting from 2 pieces of deuteron. And the last one is the process between deuteron and tritium. Okay, bigger and bigger nucleus. Okay, yes, you start from deuteron D21 and tritium 31, right? We end up with helium-42, okay, the stable nucleus or the alpha particle, and according to the balancing equation, we have one nucleon remaining here, and that's the neutron. Okay, it's not, there is no proton at all. So this is the neutron. And after that, we make the computation of the mass difference, mass of the deuteron, right here, mass of the deuterium, sorry, here, 2.014101. Okay, and mass of tritium. Mass of tritium is not available here. You need to go somewhere and pick up the mass of tritium. Okay, mass of tritium. Next one is the mass of helium-42. Helium-42 is over there, 4.002603. Okay, it's not difficult. And mass of neutron is also here, 1.00866. Okay, blah blah blah. After that, you make the summation and subtraction. You get you have to multiply at the end with 931.5. You get 17.589 mega electron volt. Okay, it's much bigger than this process. Okay, and even this process. The lightest one will be 3.27 mega electron volt. And once your element is bigger, okay, you may get like 4.0315. Okay, from deuterium and deuterium. But for deuterium and tritium, you may get the energy on the order of 17, blah blah blah. 17 plus 589. Okay, let's consider another kind of fusion process. Okay, it's not a series process, but it's quite important. This is taken from example 30.2 from the book number 1. Okay, and then we are gonna start the particle physics soon. Okay, in this one, nuclear fusion, right? Determine the energy released in the reaction of a helium-3 with a deuteron according to this equation. Helium-3 plus deuteron. Okay. Before that, we have deuterium and tritium, right? And we end up with normal helium-42 and neutron. For this one, we start from helium-32, the light version of nucleus, and the deuterium, and we end up with helium-42, the alpha particle, and one proton. Okay, so what is the energy released in this reaction? And we need to have it in mega electron volt, right? The way to compute is the mass difference between the input side and the output side, and once you get the mass difference, you just multiply it with 931.5, so you will get the released energy, right? Okay, helium-32 is the first reactant, right? The initial chemical agent. The initial agent. Next one is the deuterium, MD21, right? Next one is helium-42 and proton 11, or helium-11. Helium-32 has the mass, sorry, in the following table. What is that? Helium-32, right? Helium-32, this one, 3.016029. Okay, just take this value and leave it here, right? Next one is deuterium. So the mass of deuterium has to be later, plus mass of deuterium. Deuterium has the mass of 2.014101. Okay, 2.014101. It's positive on the left hand side, and on the right hand side is negative, right? Helium-42 minus mass of helium-42. Helium-42 here, 4.002603. Okay, this one, and mass of proton, here, 1.007825. Okay, that's the mass of the proton. And you make subtraction, deduction, and you multiply it with 931.5. Okay, 931.5. You will get the reaction energy or release energy as 18.352. Okay, 18.352. Okay, if you compare it to deuteron and tritium, yeah, the bigger and the bigger nuclei that combine together, the more you will get the energy from that process, from fusion process. Okay, this 17 and 18 right here. Okay, so the bigger the nuclei you are involved, the more the power you could get from the process, and that's the whole thing about this. All right. Next, we go to the particle physics, which is the last section of this chapter. Okay, but the lecture notes are not completely prepared. Okay, we are gonna we will do it later. Okay, let's consider this. Okay, the second section of this chapter is particle physics. Okay, actually, you have seen already the standard model of elementary particles in physics, right? That has boson, leptons, right, in quarks and so on, right? Okay, before we go to the detail of several particles in physics, you need to know the type of the forces that exist in physics, right? There are four kinds of forces in physics, right? All particles in nature are subject to four fundamental forces, which are the strong force, electromagnetic force, weak force, and gravitational force. Okay, there are four forces in physics. Okay, and the strong force is responsible for. Okay, let's consider the first type of the force. It is the strong force. Okay, strong force is somehow like nuclear force that you have seen at the beginning of this chapter. The force that try to combine several nucleons to stay together as a nucleus. Like you want to combine proton and neutrons, right, together to get the nucleus of some elements, right? And strong force is responsible for tight binding quarks, okay, to form neutrons and protons, and okay, this one is called gluon actually. And the nuclear force, right, the nuclear force that binds the neutrons and proton to form a nucleus. Okay, this force represents the glue that holds the nucleons together and is the strongest force of all the four fundamental forces. Okay, and the strong force, as the name suggests, it is the strongest one. Okay, of the four forces: strong force, electromagnetic, weak force, and gravitational force. The problem is that it is a very short range force. Okay, it's not very far. It's on the order of femtometer 10 to negative 15 meter, not 5. Okay, the number 1 is missing here. I'm sorry for that. ต้องมีเลข5ครับ 15. Okay, 15, not 15. not 5. It's going to be changed later. Okay, that's the bad thing from the strong force because it is short range force on the order of femtometer. And the next one is electromagnetic force. This is what you may have been, you may have seen, right? It is about 1 by 100 times strength of the. It's 100 times weaker than the strong force. Okay, it may not be so strong as the strong force, and the functionality of the electromagnetic force is to bind the atoms and molecules together, right? They have positive charge, negative charge, and so on. That belongs to electromagnetic force. All right. It's a long-range force that decreases in strength as the inverse square of the separation between interacting particles. So the range of interaction is bigger than the strong force, but the strength of the force reduces with the square of the separation or the distance. Okay. So the time is over right now. We are gonna finish our lecture for today. If you didn't write down your name, just write down in any YouTube channel, up to you. And we don't see each other on this Friday, right? So see you next Wednesday for M605 โอเคครับก็วันนี้ก็จบเพียงเท่านี้นะครับไม่มีการบ้านนะครับพบกันพุธหน้านะครับif you have any ถ้ามีคำถามนะครับโปรดถาม if you have any question just let me know if not then bye bye ครับสวัสดีครับthis one oh no this does stop